All right, so let's get going. First of all, I sent around a proof for that missing, that proof I put in was pretty short. And I realized it actually had a subtle error in it, too. Let me explain. There are actually two different definitions of Rademacher complexity floating around the literature, all right? The one I put into the notes has an absolute value here. And I notice a lot of people, especially more recently, do it without the absolute value. Practically speaking, it doesn't matter in the sense that all of the big results you use Rademacher complexity for will be true for one or the other one. If it's true for one, it's true for the other one. But the actual number you get isn't exactly the same. This is actually slightly bigger. And also, this is much easier to deal with. So that's why you'll notice in the notes that I sent around, there's two proofs. One for this and one for this. And this proof is actually quite a bit simpler. This one, the proof for this one looks shorter, but that's because it then calls on another theorem. But really, if you look at the whole thing written out, this is actually a shorter and simpler proof. I actually think now that I agree with people who, some people argue this is a better definition. And I think it's easier to work with, but also look what happens when you have a function set, a function class consisting of a single function. Let's see what happens. Well, we argued over here that this was going to behave like 1 over the square root of n, right? But it's still going to be positive. It'll be small but positive. What happens here if there's only a single function here, so there's no soup anymore? What is this equal to? 0, which is kind of very satisfying. That with a single function, you literally get 0. So I see a lot of people now switching to this definition, and I think I agree with them. I think it's a better definition. In fact, Jisoo's going to send around a thing about the homework that there's a coefficient somewhere in the homework. It's a very small thing. Something is less than something. And because I use this definition, I think it has to be increased by a factor of 2 or something like that. So he'll send around a notice about this in one of the questions.
Are we supposed to use that definition for?
Yeah, use either one, actually. But if you use this one, you will have to increase something by a 2 somewhere. He's going to send out a note about that. Yeah, it's a small, kind of a small technical point, but it actually just changes, small things like that. Okay, and take a look at the proof I sent around. I wrote it out in gory detail. It's not difficult, but all the steps are there. Yeah, the one in the notes is very, very short. It doesn't have a lot of the details. Okay, so I just wanted to say that. Those are, so, concentration of measure, two things, the main things are Hoeffding's inequality, the VC theorem, and what is Rademacher complexity. After that, you can look at all the other stuff as you wish. There's a lot to take in there, so I want to make sure those highlights that at least you're familiar with those things. Okay. Now I want to move on to regression. And in particular, high-dimensional regression and non-parametric regression. And you already know low-dimensional regression, so I'll just quickly remind you of the basic results. And then I want to move on to things like the lasso and talk about the theory of the lasso. Most of you have seen the lasso, but if you haven't, I'll tell you what it is. But I want to talk about some of the theory. But one difference between what I'm covering and what's in a lot of the literature is about assumptions, and this is a theme in the course, which is that I'm not going to assume ever that the linear model is correct. We'll be using linear predictors, but we're never going to assume that the linear model is correct. Just like when we do classification, we'll often use linear classifiers, but we're not going to assume that the Bayes classifier is necessarily linear. And I think in high-dimensional inference, especially, that's even more important. In low-dimensional inference, there are ways for checking assumptions. So people are used to making assumptions like linearity and checking them. You can't do that in high-dimensional inference. So I think it's really important to make sure we're well-grounded in territory where we're not making a lot of assumptions. So let's just review the basic setup for regression, though. It's a prediction problem, of course, where the y's are real valued. And we know that we have these NIID data set, the data points, training data, and we want to predict. We get a new pair. We get an x. We want to predict y. We know the best predictor in principle is the true regression function, the mean of y given x, which we don't know. And like I say, we're not going to make assumptions about it, or at least we're going to try to make as few assumptions about it as possible so that we're safe, so that we're not doing something that's relying on a lot of assumptions. Some terminology. The prediction error. Actually, there's a couple definitions of prediction error. So here's m hat, which is going to be some regression function or some predictor you're going to create from the data, from the training data. And just to distinguish these two things, there's the prediction error you would make on a new data point. So here comes new y. You predict m hat. So we're going to use squared error loss because it's the most commonly used loss. Again, it's not the only one you could use. And when we look at a prediction error like this, we can talk about it where y and x are the only random things and we're fixing this, or also over the randomness of m hat. So to distinguish those, the notation I'm using is I'm going to call the training data here D for data. So if we fix the data and look at the mean of this, the randomness is just over the new pair. So I'm saying if I give you this predictor and you use it now, what's the expected error you're going to make with that predictor? And so just to give that a name, I used a small r of m hat. And but it's also possible to talk about what is the expected value of this over all of the randomness. So now we're talking about y and x being random, but also the training data being random, which is just, of course, the mean of this. So I think I'll try to be consistent here. Use capital R for the second one and small r for the first one. Hopefully I'm consistent about this. And there's a few things you already know. Just to remind you, there's a bias variance trade-off, right, that you've seen many times, that the risk, the prediction risk has three components. What are these things? This is the unavoidable risk. That is, even if you knew the true regression function, you still can't predict perfectly. So that's what sigma squared is. So this is, if an oracle told you the best possible prediction function, the regression function, you still can't predict perfectly because there's variability. So that's unavoidable. And this is the bias, and the other one's the variance. So b of x is the expected value of m hat evaluated at x. And v is the variance. So this is stuff you already know, right? This is just the usual bias variance breakdown. And a lot of what we're going to be doing is talking about trading off the bias and the variance. Let's just review the low dimensional case before we jump into the high dimensional case. Suppose I do have a low dimensional case. Now this notion of low dimensional, high dimensional cases is in practice a little bit fuzzy, but mathematically speaking, we're imagining that we keep getting more data, n is increasing, but the dimension of the covariate is fixed. That's technically what we mean by low dimensional. So in other words, we have each x has the form of a vector, x1 to x, did I call dimension d? Yes, xd. But for the moment, for the next few minutes, d will be fixed. So there's d features per person, and there's n people. And we imagine getting more and more people. And I'm always going to use the convention that x of 1 is 1, which means I've included an intercept because we usually do that in practice. So that means that a linear predictor has the form beta transpose x for some x. Again, that's the predictor we're using, not the truth. The truth we're not assuming is linear. I should also mention this notation. So there's always a confusion in regression between, if I write x sub I, does that mean the ith person or the ith feature? But that can get very confusing in different textbooks. So what I try to do is I use the subscript for the ith person, and then I use this round bracket notation to represent the features. I don't know if that's the best notation or not. It's the best I've been able to come up with. So in other words, the ith person on person I have D features. Okay, so hopefully by using that notation you can tell the observations, which are IID, those are the XIs, they're vectors, versus the features, which are the, what you measure on each person. I hope that's clear.
Here in this, these expectation over empathic, is it with empath fixed or?
You can do both versions, actually. So this was the overall version, but you could also do it conditional, yes, on the data. All right, so if we're going to use a linear predictor, then we can talk about the best linear predictor. So I'm thinking about the places you've seen linear regression. So definitely we did one lecture maybe or 2 lectures in 705. Some of you have taken 707, which is a whole course on linear regression. 701 and 715, I'm sure you did linear regression. The point of view, though, that they did in those courses, I'm not sure. They may have written out, they may have done this, that the true model's linear. We don't allow that in this class. Don't do that. That's evil. All right. We are doing, though, the best linear predictor. What beta minimizes this? And we did do that in 705. I'll remind you what the answer is. The best linear predictor, in other words, the beta that minimizes this, the population quantity, is this. Did I call it? Let me make sure I use the same notation. Sigma, yeah, sigma. Where sigma is the expected value of x transpose. Keep in mind what this is, right? This is let's write it out. This is a x, and this is x transpose. So this is like a covariance matrix, except we haven't subtracted off the mean. The point is that this is a d by d matrix. Roughly speaking, it's like the covariances between the features. And alpha is just the roughly speaking, the covariance between y and x. So this is a scalar, this is a vector, so this is a d by 1 vector. Remember that? Hopefully you remember this. So if you just differentiate this and set it equal to 0, this is what you get. This is assuming, of course, that this thing is invertible. And the sample version of this we can get by replacing this with the training error, which is what you usually do. Let's see if I wrote down. Yeah, okay. So you would minimize the sample version of that. And when you minimize that, you get the least squares estimator. Okay, where this is now just the sample versions of everything. Right? And we proved that this beta hat, we used some elementary things, right, to show this was a consistent estimator of this beta. But this is all for fixed d, because if d was big, this wouldn't even be invertible. So that's why it's the low dimensional world we're still talking about. Okay, so that's a review of basic linear regression in the low dimensional case. It's very simple. And the way to think about it again is beta hat is not estimating the true regression function, it's just estimating the best linear predictor. Okay, any questions? Good. All right. I threw in a couple of theorems that might be interesting for you there. They're not critical for us, but They just they're bounds on how close is this. When you do least squares, how close are you? Can you say something about how close you are to the best linear predictor? And that's what theorem 1 and theorem 2 are different versions of that statement. The proofs are only using, I didn't put them in because they're very long, but they only use the tools that we've discussed so far in concentration and measure. I did put the references if you're interested to look at it. But the important thing to notice is that the error is of order d over n. So if you look at theorem 1, you see basically that the risk, or theorem 1 or theorem 2, the risk of the least squares estimator compared to the risk of the true best linear predictor, something we're estimating, has an extra term that, due to estimation of order d over n. And I'm just pointing that out because, again, you see where the role of dimension comes in. If d is fixed and n is getting bigger, you're paying a small price for having to estimate the best linear predictor. But obviously, if d is big, you can see that it's not going to do very well. And in particular, the estimator won't even be defined when d is bigger than n. So that's why we want to talk about the more interesting case, which is high dimensional linear regression. So high dimensional could mean a few different things. It could just mean, at a technical level, we could imagine that as n increases, d also keeps increasing. But we could also imagine an even more extreme case where d is strictly bigger than n, which now is very common. It's changed quite a bit. When I was a student, which is ages ago, we never saw data sets where d was large. 5 was considered large. 10 was huge. I'm not kidding, Now we do have data sets where you have maybe 200 people, but you've measured 5,000 genes. So d is huge, and it's much bigger than n. These are just, you guys take this for granted because this is the kind of data you've heard about. But it's a pretty recent phenomenon in some sense, this high dimensional stuff. And so the question is how to deal with it. And there's a lot of literature on this, but I would say I'm going to divide the world into kind of a few approaches. So one is, if we go back to the minimization problem we're doing. If we try to minimize this now when d is very large, you're going to have a problem, because of the non-invertibility. But there's another way to think about it too. There's a bias variance trade-off, and when the number of variables gets larger, the variance just keeps getting bigger and bigger and bigger. So an older way of dealing with this, which we in statistics and in machine learning, we call it ridge regression. In the signal processing world, I think Tikhonov regularization was probably the term people, maybe they still use it. But it's basically just add a penalty term, and specifically the norm of beta squared. So what's the effect of this? Well, first of all, there's a parameter we'll have to pick. And when we talk about estimating risk, we'll be thinking about the prediction risk as a function of this lambda, and we'll use cross-validation to estimate the risk, and we'll try to minimize it over lambda. So lambda is a tuning parameter that we're going to pick by some version of cross-validation. The effect of the penalty is what? Well, if you try to make, let's imagine lambda is pretty big, so this penalty really matters. If you try to put huge betas in here, you're going to get a big risk now. So that's going to favor taking beta close to 0. Basically, it shrinks the estimator towards 0. So as lambda goes to infinity, in fact, the betas are going to go to 0. Conversely, if lambda is 0, we're back to the least squares solution. So a typical picture would look like this, that if I have lambda here, let's suppose for the moment that we had d less than n, so the least squares solution was well defined. What would happen is that when lambda is 0, we get, if I put beta 1 hat, beta 2 hat, beta 3 hat, beta 4 hat, whatever, if I put the beta hats, that's the least squares solution if they were well defined. Then as I increase lambda, these all kind of shrink towards 0. And if I plotted the prediction risk as a function of lambda, there's going to be some sort of bias variance trade-off. If I shrink them too much, it's going to be very biased. If I don't shrink them enough, I could have a lot of variance. And so the idea would be to use cross-validation. We'll talk about cross-validation in more detail, but to try to estimate this risk and pick the best lambda. So I'm sure, who has seen ridge regression in one of those courses? Some version of ridge regression. Not everyone. Okay. I thought everybody had seen it. But if you haven't seen it, that's okay. Now you've seen it. The nice thing about it is if I minimize this, because everything here is differentiable and so on, we can write down exactly what the estimator is. It's just beta hat plus sigma hat plus lambda I inverse times alpha hat. So the only thing that's changed is where we had lambda hat inverse, now we add lambda times the identity matrix. That makes this invertible. You can think about it from a numerical point of view. You're just regularizing sigma hat to make it invertible. Or think about it as from the statistical point of view, by adding this regularization parameter, we get a tuning knob to control bias versus variance. Large lambda gives you a lot of regularization, pulls the betas towards 0. That's going to make the variance small. But whenever you make the variance small, you make the bias bigger, and vice versa. And so this is an older solution. It's been around for a very, very long time. It's still a good solution. So we're going to talk about the newer methods, but you shouldn't forget about ridge regression because it's often a very good predictor. And so this is a viable method, and it's easy to do, and so on. Okay, question?
What's the intuition for why adding something on the diagonal makes it invertible?
Oh, well, if you look at the eigenvalues of this thing, lack of invertibility happens when some of the eigenvalues go to 0. You're now adding a constant to all the eigenvalues. That's intuitively what you're doing. You're making it more well-conditioned.
How does the size of the betas relate to variance?
How does this? So why is small betas lower variance? Is that what you mean? Oh, so yeah. So let's see. I have actually a theorem about that written down, but we could actually. I didn't do that here. If you were to compute, this is an interesting exercise actually. Since we have a closed form, you could compute the bias and variance of this. And you would see that as I regularize more, pull things towards 0, the bias goes up like this. That's the bias. And the variance goes down. The intuition for that is, let's just think of the extreme case. If I make lambda go to infinity, beta 0, so my estimator is 0, it's a constant. And a constant estimator has no variance. That's the intuition for why the variance gets smaller as I regularize more. But there's a homework question where you did shrinkage. So this is a type of shrinkage, meaning you're pulling the estimators towards 0. But you did a question in the homework about using an estimator like that. And as what you saw there, when A is 1, you got an unbiased thing. But when you make when you shrink it towards 0 more, it reduced the variance. Shrinkage always reduces variance and increases bias.
So that means that lambda has to be like bigger than the minimal eigenvector is.
Well, actually, the optimal lambda. So let's look at. I included a theorem here. Surprisingly, only from this is results from 2014. So the general results on this, I was kind of shocked. This was the best thing I could find. It's the paper of reference there in theorem 4 gives what is the risk of the ridge estimator compared the predictive risk of the ridge estimator compared to the best linear regressor, which we never know. And you can see it looks kind of complicated, but let me just pull out the main terms here. It's lambda beta squared over 2 plus sigma squared over n trace of sigma over 2 lambda. So what you're seeing here is kind of the bias variance trade-off. You see a lambda is upstairs here and a lambda is down here. And so you could ask, what is the best lambda? Well, you could just minimize this over lambda. And you're going to get something which involves trading off the size of the coefficient, because if the size of the suppose beta was 0, the best linear predictor was 0, this term wouldn't be here. You might as well take lambda to be infinity. That corresponds to what? Shrinking all the way to 0. Well, of course, if the true beta is 0, the true beta meaning best linear predictor is 0, the best you can do is set beta equal to 0. Right? So that's sort of coming out automatically from this. But if there's more signal to that, so to speak, then that wouldn't be optimal, and there would be some sort of trade-off here now. This is like a variance and a bias, and you can see how they trade off. This formula is not something we use to choose lambda in practice. You're going to have to use some version of cross-validation, because there's a lot of, obviously there's unknown quantities here. But it gives you a theoretical feeling for how these things trade off, that there's a bias variance trade-off. And the optimal lambda from this formula, the answer is given theoretically right here, to the degree at least that this bound is tight. I think it's pretty close to tight, probably. I should have said one other thing, is that I always treat the x's here as random. There's two worlds in regression. I mentioned this in 705, that I always treat the x's as random variables. It's an odd thing that there are a lot of papers, surprisingly, treat x as fixed and y as random. Why would people treat x as fixed? I think I think there's two reasons, actually. So historically, when this stuff was created, when people were doing this in the 20s and 30s, people were doing experiments in factories, and they were literally setting the x's. The x was like, what temperature am I making this aluminum at, or something like that. They were doing experiments in factories or agriculture experiments. They were literally choosing the x's. They weren't random variables. Somebody was setting them in the laboratory. And so from that experimental world where statistics really grew from, x literally was a fixed thing. It wasn't a random variable. But most of the data we get these days is not like that. You get millions of gene measurements and so on. No one's fixing them. They're just random variables. The other reason why people thought of x as fixed is there was a lot of results in the 60s in mathematical statistics about the fact that even if the x's were random, there was something optimal about conditioning on the x's and treating them as if they were fixed. But all of that literature assumed that the model's correctly specified. So once you leave the world that the x's are being set by an experimenter or that you know the model exactly, I don't see any reason to treat the x's as fixed. I think it's a very odd assumption. And so I try not to make that assumption. I think one of the reasons why results like this are new is because these results are under the assumption that x is random, whereas you can find much more older results about what happens if x is fixed and the model is correct. Whereas these results are saying x is random and the model is incorrect.
So what about if it's not that I have experimental data, but I'm planning an intervention and I'm going to change the distribution of x?
Well, now, of course, as you know, we're getting into a whole world about causal stuff, which would be fascinating to discuss, but is a whole, I mean, it's going to be a whole other can of worms. So I'm right now really just talking about the pure prediction framework. I mean, those are interesting questions, of course, but they're complications. So I'm dodging that question. Okay, so the other thing I want to say is it can be shown that if the linear model was correct, and if the errors were normal, if you had y equals x beta plus normal errors, and if you put a prior distribution on beta that was normal, and you computed the posterior mean, you would get back the ridge estimator. So there's a Bayesian interpretation of ridge regression as well, which is mentioned right at the proposition 5 there. Okay. So ridge regression is nice and simple because it has a closed form solution and it's very easy to study it. I mean, admittedly, these results, actually the proofs, if you look at, are fairly complicated, but the basic idea of getting the mean and variance of this estimator is fairly simple just because we have a closed form solution for the estimator. Okay. However, ridge regression is not, I don't think, the favored method these days for two reasons. One reason is it does not give you a sparse answer. That is, although you're shrinking all these beta hats towards 0, it doesn't set them literally equal to 0. And yet, people would often like to have a sparse beta hat. They would like to have many of the beta hats equal to 0. Why? Why would we like to have many beta hats? So let's say I do 5,000 genes. I do my regression. People want to get out a regression estimator, a predictor, where maybe only 20 of the beta hats are not 0. And one reason for that is simply because of efficiency. That suppose I'm going forward, now I have to make predictions. If only 18 of the beta hats are non-zero, that means in the future I only have to measure those 18 genes on everybody. Right? So for very practical reasons, it would be very convenient to have a sparse predictor. It would be very convenient to have a beta hat which has many zeros. So it might look like some number here, then a 0, then some number here, then a 0, and so on. Lots and lots of zeros. So you can see that in terms of storage, in terms of what information I need to collect in the future. It would be very convenient to have a sparse predictor. Ridge regression does not do that. Ridge regression, you're going to get many, many small betas, but they're not going to be 0. So there's a lot of interest in getting sparse predictors. Another reason why people want to get sparse predictors is they might believe the truth is sparse. That one's a little bit more questionable to me. I think that's more of a hope than a scientifically justified belief. But for practical reasons, it does make sense that you might want to get out a sparse predictor, a beta hat with lots of zeros in it. Okay? So that's why I think that a lot of the attention lately, and probably what you learned in 701 or 715, was things like L1 regularization, or the lasso. But before we introduce that, how many of you have seen the lasso? Okay, probably almost all of you. Okay. I'll remind you what it is, though. But before we get there, let me backtrack to how we get to the lasso, which is variable selection. So there's another solution to this problem of having too many variables. Instead of shrinking them all, an obvious thing is choose a subset of them. So what we would do is somehow use the data to choose a subset S of the covariates. Say pick 10 of them or 11 of them. And then we can talk about, let's call it X sub S, which is just, all I mean by that is the covariates corresponding to that subset. And now we just do regression on that subset. So there's now a best beta, namely the minimizer of y minus xs transpose beta squared. This is just choose 10 genes and now do regression on those 10 genes. This is probably even older than ridge regression, which is just choose a subset of the variables, or at least as old as ridge regression, maybe even older. And it has the advantage that it's sparse, right? If I say I'm only going to pick 20 variables, then by definition I'm going to end up with 20 variables. And this is called best subset selection, actually. If I try to choose the best subset, then it's called best subset selection. We don't want to pick any, we don't want to pick 20 random genes, right? We want to pick the 20 best ones. So we'd want to minimize this not only over beta, but over all choices of S. Okay, well, there's two problems with that. So suppose we have, let's suppose we decide on the number of covariates I'm going to use. That itself is something we have to choose. But let's just suppose from I've decided I'm going to use 10 covariates. So I want to regress on some 10 covariates. We know how to do that, but how do we pick them? So the natural thing to do would be to minimize the training error but subject to the constraint that the beta you choose can only have 10 non-zero elements. So the way we usually write that is that beta 0 is less than or equal to, so k here is however many non-zeros we want. And beta 0 is a quasi-norm. It's not really a norm, but it's just defined to be the number of elements of this that are not 0. Okay, so technically in best subset variable selection, what we would do is no problem. We just minimize, like we did for least squares, subject to a constraint that the 0 norm is no more than 10, or whatever number we've picked. Okay. So that's great. That's best subset selection. You can actually do this if you only had 20 variables and you're trying to pick the best 4. You could actually do all 20 choose 4 things and compute them, but it gets out of hand pretty quickly. This is NP hard. Now, I'm not a computer scientist, but I know enough computation to know that when something's NP hard, forget it, right? That's too hard to do in practice, at least when they have a large enough number of covariates. So we have the kind of problem that, we can state the problem we want to solve, but it's not clear, how to proceed. And so there's two main solutions to this problem. So the problem is that we can't solve this exact problem. So we either solve a different problem, or we modify it, or we approximate it in some way. So there's two approaches here. The older approach, whenever you have a very difficult problem, one possibility is to try some sort of greedy approach, which in statistics, this is what's called forward stepwise regression, which I'll explain in a second. And again, when I was a student, this is what we did. This was the most common way to deal with variables, is we're going to add them in one at a time. If anybody here a signal processing person? Just one or two? You may have known it under the name of orthogonal matching pursuit, right? That's orthogonal. I always get the two mixed up. Yeah, orthogonal matching pursuit. What we call stepwise forward regression, basically, in statistics. But then along came, in 1995, Rob Tibshirani's paper on what's called the lasso. I never liked the name. I told Rob it was a stupid name. He didn't listen to me, because I can never remember what it stands for. Least something, shrinkage, selection, something. I can't even remember what it stands for. And it's too late to change the name now. What was it? Least absolute shrinkage selection operator. I mean, he had this idea that it was like, cowboys have this lasso and you reach out and you grab some variables. And then I think he tried to make up the... here's a little story for you. Just never take investing advice from me, because I remember the day when Rob's an old friend of mine. So he called me and said, I have this idea. And he explained this to me. And I said, that sounds OK, but I don't think it's a big deal. Completely changed the direction of statistics and machine learning. So apparently I cannot predict the future very well. And don't take any practical advice from me. But I think I was right about the name. It's not a good name. But anyway, what we're going to do is do a convex relaxation of this. For those of you who have seen this before, which is most of you already know this. These days, I think the lasso is preferred to this because it's easier to study. It's not necessarily computational. I guess computationally, it's about the same difficulty as forward stepwise. Maybe it's considered a cleaner solution. It's not, as when I show you the main results about these, you're going to see that they have the same rate. So the theoretical guarantees are the same. But it seems like there's a lot of practical advantages to the lasso. OK, so So let me say, the one I really want to emphasize is the last. So I just want to say what forward stepwise does. And for your information, I've included some theoretical results about forward stepwise. They usually get ignored. But there are comparable results for forward stepwise. I'm not going to go through them. And they're only there if you're interested. They're a little bit, to be honest, they're a little bit more complicated than the lasso theory. We're going to prove the main lasso theorem, and you're going to see it uses very elementary concentration ideas. To do the same thing for the forward stepwise, I've even had a lot of the material in the appendix and so on. It's actually just, the proofs are much more complicated, even though they end up in roughly the same place. But let me just tell you what the basic algorithm is. It's very simple. If you haven't seen it before, you have your y, and then you have your features, let's say x1, x2 to xd. And I should say the first thing you usually do when you're doing variable selection is we usually standardize the x's. So like we subtract off the mean and make them all have variance 1. That may or may not be a good thing to do, by the way, because some people will argue that the variances of the x's are actually informative. That may be things with, so for example, as an extreme case, if this had 0 variance, if this was a constant, that's not going to give you much information. So some people actually use the variances for selection. For simplicity, though, when I describe the algorithm, I will assume the variables are standardized. So each column of all the x's is going to have mean 0, variance 1. You just make the expression simpler. And so step 1 is this. I say, if I had to throw one variable in to do regression, which one would I pick? Well, I just look at the correlation between this one, this one, this one, this one. So you look at all the correlations, which I'll write like this, y, xj, which is the same as saying I'm looking at the regression of y on each variable, because I've standardized it. If I wrote out the regression, a one-variable regression, there's some other terms in there. But when you standardize the variables, the beta hat is nothing other than the correlation between y and x. That's why I wanted to standardize it, just to make it look simpler. So anyways, you find the most correlated one. And now what you do is you take what's called the active set. This is the set of variables I have so far, which is empty to start with. And let's suppose that let me try to stick to the notation here. I called that J. Yes, so let's suppose that, well, let's just do an example. Suppose I do this and the variable 15, feature 15 is the one that's most correlated. So now I include that into my model. My model now has one variable. Now I do regression. So now you can do regression. You regress y. Let's write it like r. Y on x15. That would be the r command. Okay, whatever it is in MATLAB, I don't know. I'm doing the regression of y on x15. And now you get the residuals. So the residuals, you remove the effect of beta hat 15. That's now what's left over after I've regressed on 15. And now you repeat. I take the residuals now, because the residuals are what's left is the unexplained part, the part that we haven't explained yet by doing regression. And I take the correlations again, and I say which one is the most correlated with the residuals. Let's suppose it's 83. So now I include my model to be the first variable and the second variable. Now I have two variables in the model. Now what do? Now I repeat the regression from start. Okay, so now I do a new regression of the original variable on both of these. I do a regression with two variables in it. Then I get out the residuals again. In this case, it's going to be y minus beta hat 15x15 minus beta hat 83x83. But it's one very important point here. I'm not going to get the same coefficient now because I'm doing two variable regression. So you're redoing the regression now. We're projecting, in other words, onto the span of these two variables. Now I repeat. I get the residuals from that. I say which variable is most correlated, and I add the third variable and so on. Okay? Is that clear? It's a very simple algorithm. So one of the nice things is it's very simple. You don't need to know convex optimization to write code to do this. That's one of the nice things about forward stepwise regression. Is this linked to PCA? Not really. It's solving a slightly different problem. I mean, PCA is similar. It's similar to regression, but it's not quite the same thing. Does the order matter? Well, it's picking an order for you. It doesn't, the order of, if I permuted these, it wouldn't change the output. But it is picking a particular order. And yes, what I picked before will affect what goes in next. So in other words, when I go to pick the fifth variable, what I put in before will affect what I choose as the fifth variable. I mean, this is the thing about greedy algorithms, right? It's not the same as minimizing. The answer I get here is not the same as minimizing over all pairs. That's how we're avoiding the NP-hard problem, but by doing it one variable at a time. But we're not going to get the same solution as if I just solve the original problem. But you can relate it to the best linear predictor. That's what the theory in here is about.
Do you decide what to stop just based on?
So yeah, when we get to cross-validation, we'll talk about that, because now you need to choose how many variables should I include. And what we're going to end up doing in practice when we talk about cross-validation is we'll estimate the prediction error as a function of k, and that's how we'll choose how many variables to put in. Yeah.
Is this something like a submodular optimization procedure?
So yeah, I think it's not submodular, but there are people who have proved results about forward stepwise assuming submodularity. Then you can say more theoretically about how it behaves. Very recently. So if you type forward stepwise regression or greedy regression submodularity, you'll see some results like that.
Do you only care about the bias in this case?
No, this is supposed to be the prediction curve.
Oh.
We always care about the bias and the variance. How well do we predict in the future?
Is there any kind of difference if we're computing the correlation using some kind of like standardization version to the mean or something like that?
Sorry.
Because the correlation is defined just as the multiples of x and y, and after that you just take the average of that. So there's
So that's because I assume they were standardized. If you didn't standardize it, you can't just take the inner product. You actually need to do a full regression. You have to add it into the regression and so on. Yeah, so that was just for expedience that I did that. So that's, again, this is an old solution, but don't dismiss it. These old things like ridge regression and forward stepwise, they might work well in your problem, right? So don't give up on them. I think people have given up on forward stepwise too quickly. The lasso kind of wiped it out. But there are probably cases where it's a good thing to do. And again, it's very, very easy to program, which is nice. It's also easy to add constraints. If you decide I want to add some sort of constraint, I had a student working on a biological problem that when he wanted to make sure that the variables actually had spatial locations, and he wanted to make sure that you didn't get two variables close together. So he could do forward stepwise. When he added in a variable, he made sure that the ones he added in next weren't allowed to be too close to the previous ones. So adding in extra constraints like that is very easy in forward stepwise, not so easy necessarily in an L1 framework.
Are stepwise and stagewise sort of synonymous?
So stagewise is something I haven't mentioned. It's not exactly the same. Think of it as a slight variation of this. It's more closely related to the lasso in some sense. I'll talk about the relationship actually between them in a minute. Okay, so what I really want to get to though is the lasso. Let's see, how are we doing on time? Okay, we're good. Any other questions about forward stepwise or greedy regression? Okay, that's all you need to know about it. But if you are interested in the theory, I spent some time putting it all in here. I don't know why, since I'm not covering it, but I just thought people might be interested in it. There's a beautiful little theorem due to, I don't know how to say his name, Temlyakov. He's this Russian guy. He's got a lot of results about greedy approximation, which just shows you, first of all, in the noiseless case, that's theorem 7, if there was no noise, how would the error decrease as we add in more and more variables? And then extending that to the noisy case, the real world case is fairly complicated. And there's a theorem about it, theorem 10, with the proof offloaded to the appendix. And even there you're going to see I have to refer to other theorems that aren't in here. But the noiseless case, the proof is very straightforward. You might want to look at that if you find this interesting. And then the noisy case uses concentration of measure to argue that the noisy things are close to what you would get if there wasn't noise. And the main result I want to mention, so I'm not going to go through the theory because it's very long and I'm not sure how many people would be interested. But if you ask yourself, how close do you get to the best linear predictor based on k variables? So we have this greedy thing. We're going to do k steps of this. But you could imagine an oracle which says, suppose I got to pick the k best things in terms of the best linear predictor. How close do you get? And if you just look at theorem 10 on page 10, what it says is, this is the, I've been using m for predictor, and for some reason in this theorem I used f. But the distance, this is just the L2 distance between what you get from the algorithm and what an oracle would get, which I called, I'm reading the wrong theorem. Theorem 10, that's it. And yeah, here it is. This is after n steps of the algorithm times a constant plus something like log n over root n. What this is saying is that forward stepwise gets to about within 1 over root n of what you would get if you could do the perfect best subset selection. That's in squared terms. If I went back on the original scale, so if this is squared, if I take the square root, the rate is going to be like n to the 1/4.
What is that?
That's the best, that's the true regression. So let me call them m. This is the true regression. This is what you get out from your stepwise. And this is the best predictor based on n variables. So a few things to note about this rate. So again, if we went back from the squared scale to the original scale, it's n to the 1/4. That's an unusual rate. That turns out to be optimal. You can't beat that rate without adding lots of extra assumptions. We're going to see we get the same rate from the lasso. We're going to prove it in the case of the lasso, using very simple concentration ideas. Something else to notice, though, is the dimension hasn't shown up. Maybe you would expect that the dimension of the regression problem, we're dealing with a high dimensional regression problem, why doesn't that show up anywhere here? But that's because we're not saying we're approximating the true regression function. We're approximating the best n-term or k-term linear predictor. That's a weaker claim. That's why the dimension doesn't show up. When we talk about non-parametric regression, where we try to really estimate the true regression function, then we'll get the cursive dimensionality. Okay. Okay, so that's forward stepwise, greedy. So let's now talk about the one that everybody uses mostly. Which is the lasso. So let's write it this way. So let's remind ourselves what the kind of idealized problem was, which was we wanted to minimize the training error subject to the L0 norm being bounded by some number. So the idea of the lasso is to say, instead of using the L0 norm, what if I switch? I'm going to use the L1 norm. What's the L1 norm? So this is kind of in between the ridge regression, which uses the L2 norm, and best subset selection, which uses the L0 norm. Okay? And this is our minimization problem now. Minimize this subject to this. So why the L1 norm? Well, first of all, let me point something out. Did anybody here take the convex optimization class? Or just a few of you? Well, that's a great class. Those of you who haven't taken it, I highly recommend it. And a lot of the properties of the lasso are studied in that, because this is a convex problem. I'm not going to talk about all the properties that arise because of the convexity. I'm not an expert in convex optimization. But yeah, that's the class to take if you want to know all that stuff. But first of all, one simple result is that you can show that doing the minimization subject to this constraint is the same as just adding on the penalty. That's the Lagrange form of the minimization. In other words, if I had solved the previous problem for every value of k, I would get a whole sequence of solutions that depend on the amount of penalty I'm putting on. Similarly, if I solve this problem for every value of lambda, I'll get the same sequence of solutions. So you'll see it written in either form, either as minimize this subject to the L1 norm being less than something, or just minimize this sum. Okay, you end up with the same set of solutions. So sometimes I'll write it one way, sometimes I'll write it another way. Why the L1 norm, though? This is a very interesting question, and it's critical to all of this. So there's a couple of answers to that. Well, one of them is, one intuitive way to think about it is we really would like to use this L0 norm, but that's not convex. So we're trying to use a norm that's in some sense as close to L0 as possible that makes this convex, and this is a convex problem. You can think about the convexity in terms of what the neighborhoods look like. So if I look at vectors, like what does this look like? The L2 norm, let's say less than or equal to 1. And let's just do two variables, beta 1 and beta 2. So this is just beta 1 squared plus beta 2 squared less than 1. Well, what is that? That's just a sphere. Right? If you look at the L1 norm, you get this diamond shaped thing. And notice that the neighborhood is a convex set. We're in the convex world. That's always the separating thing, apparently, right, between what's easy to, or fairly easy to compute and not easy to compute, is whether you're staying in the convex land or not. And this is convex. In fact, you can define, of course, the norm for other. We could look at the beta p norm. Remember what that is. And if you take p small, let's say p is like a half or something, between 0 and 1, and draw the set of all betas where this is less than 1, you're going to get this weird it's not convex. And beta 0 really just corresponds to basically coming down to the axes. So we're trying to get close to the beta 0 norm, but keep it convex, so you kind of end up with beta 1. That's one way to think about the L1 norm. But here's another point. You notice that this has corners. In fact, so do these. Whenever p is less than or equal to 1, you get corners. Corners are what makes the solution sparse. Why? Because I'm not going to, the proof is in the convex optimization class, but I'll just give you the picture. So this is proof by picture. If you think about minimizing this thing, what is this? This is some quadratic function. Let's again do a two-dimensional picture. So here's the least square solution. If we're only in 2 dimensions, we can assume the least square solution exists. And we're trying to minimize this function. So these look, this has the contours of this function maybe look like this. So you think of the function as being 0 here and growing like a bowl-shaped thing. But we're minimizing it over this set. We're doing a restricted minimization. We're trying to take this function, which is 0 here and grows like a bowl, but we're only minimizing it over here. And if there's corners, I didn't draw this very well. Eventually, subject to artistic error, you can convince yourself that if the configuration is right, that the minimum will tend to occur at these corners. The corners play a big role. This is something that can be proved. This is not proof, but it can be proved. But what does that mean? When you hit a corner, some of the betas are 0. This is why you get a sparse solution when you do the lasso. It's the corners.
What if it doesn't hit the point?
Then so what's typically going to happen, really, don't forget we're in high dimensions, is it'll hit corners in some dimensions but not in others. And so what's going to happen is some of the betas will be 0 and some won't be 0. And you can show that as you penalize more and more and more, you're going to get more and more zeros. So increasing the L1 penalty gives you more and more zeros. Not monotonically, but eventually. I'll draw a picture of the solution path in a second. So again, all these numerical properties are studied in the convex optimization class. I just want to give you an idea of what's going on. You can see the same thing would happen for other norms, like p equals a half. You're going to get sparse solutions. But again, that would be non-convex. So if we want to get this compromise of convexity, but we want to have corners, we want to have sparse solutions, we're back to L1. L1 seems to be just right in between everything. At the edge of what's computable, but what also gives us these properties that we want. L0 would just be things along here, 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 and here. Yeah. Okay, so this is, I want to give you one other piece of intuition about the L1 norm. Another reason for using the L1 norm is we could ask, well, is there a norm which gives us convex neighborhoods, but which is somehow sensitive to sparsity? What do I mean by sensitive to sparsity? Well, let's consider, let's consider a few vectors. So let's suppose I have a vector that looks like, 1 over root d, 1 over root d. Now I want to take 1, 0, 0, 0, 0, 0, 0, and 1, epsilon, 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 where epsilon's a tiny positive number. Yeah, let's consider these 3 vectors. Okay. Now let's look at the norms of these vectors. Let's call these vectors A, B, and C. And I want to look at the L0 norm, the L1 norm of the vectors, and the L2 norm. What is the L0 norm, the number of non-zero elements? D. So it's big. So that's good. I'm trying to see if I can capture the fact that this is not sparse. What is the L1 norm? So if I take the absolute value and sum it, get root d, right? What is the L2 norm? If I square it, sum it up, take the square root, 1. Okay. Now let's do this one. What's the L0 norm? 1. L1 norm? 1. L2 norm? 1. L0 norm is d. The L1 norm is about 1 plus epsilon d. And the L2 norm is whatever that is, 1 plus d minus 1 epsilon squared, square root, something like this, right? Let's see which norm is capturing sparsity. So I would consider this sparse. I want this to have a small norm if my norm is somehow capturing the idea of sparsity. So the L0 norm clearly works. Right? It's saying this is sparse. Sorry, I did it the wrong direction. No, that's right. The L0 norm is correct. The L1 norm is correct. It seems like this one might be okay, but the problem is the L2 norm doesn't distinguish these two cases. From the L2 norm's point of view, these have the same norm, but clearly this one is sparse and this one isn't. So L2 fails to distinguish that this is a sparse vector and this isn't. And similarly for the other one. So here, I don't know why I included this one so much. This is the main comparison here, that L0 works to notice that, but L1 also works. It's saying that this one has a much higher norm than this one. So L1 also notices that this is less sparse than this by making the norm bigger. L2 doesn't. You can forget the third one. It wasn't that essential. So I'm just trying to get across the idea that the L1 norm has convex neighborhoods, but it is sensitive to sparsity. Things that are not sparse have bigger L1 norms. Hence, when we penalize by that, we are penalizing lack of sparsity.
This might be out of the scope of discourse, but is convexity essential?
Is convexity essential? That's a very interesting question. You know, to the optimization people I talk to, they'll say, well, it's really important because we know how to do convex optimizations. When things are non-convex, it doesn't mean you can't solve an optimization, but it's much harder typically. Of course, there's a lot of interest now in non-convex optimization. But it certainly does seem to be a dividing line, right, between things that are considered doable and things that are considered sort of a whole order of magnitude more difficult. Okay, so that's just some intuition about why you'd want to solve this lasso problem. But it's going to be a convex optimization, so we know there's software for doing it. And we also know that it's going to give us a sparse solution. Oddly enough, one of the ways of solving this problem, though, is something somebody mentioned, which is a stage-wise method, which is very similar to forward stepwise regression, except in little increments. And so, oddly enough, there's an algorithm for solving this problem. There's many different algorithms, but one of them kind of mimics a kind of smoothed-out version of forward stepwise regression. So forward stepwise and the lasso are often not as different as you might think they are. But there are certainly examples where they give you different results. There's lots of examples I've tried them on, though, where you get very, very similar results. All right, so what I want to talk about, though, is the theoretical properties. And I want to mention three main theorems, one of which we're going to prove, the important one. I call it the master theorem for the lasso. The first two I'll just tell you about, and the third we're going to prove, and I guess today I'll just tell you about them. The next week we're going to prove the theorem. It's a really, I think it's a very, very interesting theorem. So what can we say about this? So there's three types of results. Three types of main results. I mean, there's a trillion papers on this now, but sparsistency, consistency, and risk consistency. So let me explain what these are. Sparsistency refers to the following things. Suppose the true model is actually linear. Suppose that the beta is actually, the true beta is sparse. And let's define the support of beta to be all the places where it's not 0, some small set. Then sparsistency says that the probability that the estimator has the same support so these are the non-zero, the places where this is non-zero, this is of the estimator of the truth, and if the probability of that goes to 1, then we say it's sparsistent. It's getting the right sparsity pattern. And there's a lot of theorems about that. I've quoted a particular version. So intellectually and mathematically, this is important and interesting, but practically speaking, I think this is very, very uninteresting. And the reason is the following, because let's look at the list of assumptions you need to prove this. Assumption 1, the true model is linear. To me, that's a game killer right there. I don't care about that. And that's just not going to happen. All right, it gets worse. We also have to assume something about the correlation between the features, and this is sometimes called incoherence or incompatibility or restricted eigenvalue conditions. Basically, you have to assume that the features, roughly speaking, are close to uncorrelated. And you can see why that would be true, right? Suppose the true model was y is equal to 5x1 plus noise. But suppose that x13 and x1 were virtually equal, very correlated. You'll never know whether, you'll know there's a big regression coefficient out there, but is it x13 and x1 just happens to be correlated with x13? Or is it x1 that's got the big beta and x13 is highly correlated? If two things are very correlated, you're never going to separate them. So you need a condition, which is basically that they're not correlated, in order to do this. And it's a completely unrealistic assumption, except in certain cases. So in signal processing, actually, where you are often in a situation where you get to generate the X matrix. You can generate an X matrix which is incoherent. You can create an X matrix where the columns of X are very close to independent, if it's under your control. But if someone's just giving you a pile of data, here's a bunch of Y's, here's a bunch of X's from the real world, I can tell you, I've never seen in my life, in the years I've been a statistician, a single regression problem that came close to satisfying these incoherence conditions. Real data, everything's correlated. And there's outlier, I mean, real data are messy. And this is a very, very kind of pristine assumption, which is, it's useful for doing theory, but it's a mistake to then proceed and analyze real data as if this assumption was true. So that's the second assumption I'm complaining about. You have to make, the amount of penalization you have to do has to be chosen very carefully. And in fact, if you look at the theorems on this, the lambda is chosen for the theorems using knowledge of the true beta, which is, you can't do that in practice. So there's all kinds of problems, in my opinion, with these results, which is not to suggest, again, they aren't theoretically interesting, just that their practical import to me is very limited because I just don't think the assumptions are very realistic. Similarly, there's consistency results that look at the vector of betas and ask, does that L2 norm go to 0 in probability? Remember in 705, we often proved theorems about parameters converging in probability to 0 to the truth. But it's the same problem. You need all this long list of similar assumptions that are just never going to hold in practice. The worst of which is that the true function is linear. And these are assumptions, by the way, that are not testable. And to see why they're not testable, we're starting with what is essentially an ill-posed problem. Right? You've got more variables to estimate than data. That's an ill-posed problem in some sense. The solution to prove these theorems is to make enough assumptions to make it well-posed. But if you make assumptions to take an ill-posed problem and make it well-posed, by definition, the assumptions aren't testable, or it wouldn't have been ill-posed in the first place. Okay? So you'll never even be able to test these assumptions. So by all means, look at the theorems, and if you're interested, you can certainly follow up on them. Just don't think of them as being true when you're actually analyzing data. But the last theorem is, oh yes, question. Now this is a really cool theorem because this says that with high probability, the predictions you get from the lasso are going to be very close to what you would get from the best sparse linear predictor, which we'll define either in a minute or next week. And we're going to see, again, using basically no theorems. The history of this, though, is kind of interesting. So that I'm going to just prove a simple version. There's a more general version in this paper I referenced here by Greenstein and Rithoff. But actually, the first proof of this goes back to, I think it's Nemirovsky, Duditsky, if I remember it. A paper that's been very much overlooked because they don't mention the lasso in it anywhere. It's just some paper with a bunch of theorems in it that they thought were interesting. But it turns out it's exactly, if you look at what they're doing, it's exactly the lasso. Maybe they didn't know about the lasso or something like that. And they cast it much more abstractly, but it turns out turns out to be proving this. So there's kind of a rediscovery of some older ideas here. So what do I mean by the best sparsity linear predictor? Well, we're talking about L1 sparsity. So I'm defining, let's say that, let's look at the constrained version of the lasso. We're solving this numerical problem. we're minimizing that over beta, subject to some L1 norm on beta. So we're going to accept the fact that we're using the L1 norm to characterize sparsity. Well, what would the population version be? What would be the best you can do? Would be to minimize prediction error, the true prediction error, subject to that constraint. We'll call that the best sparse linear predictor. So this is going to give us an estimator, and this is something we can't ever compute, but it's the target, it's the population target. So just like in low-dimensional regression, we talked about the best linear predictor. Now we're talking about the best linear sparse predictor. And so what we'll prove next week is this theorem, that the risk of this thing comes very close to the risk of this guy, which I call the master theorem. Then the other thing I'm going to show you next week, though, is a little bit surprising. And it's one of the dirty secrets that you don't hear much about this. But there's a price to pay for sparsity. Remember we talked a little bit about minimaxity in 705, and we're going to talk about it again later in the course. Sparse predictors have terrible minimax error. And we're going to prove that because it's actually not so hard to prove. And this is another one of those things that, I don't know, everybody sort of pretends it's not there. I didn't ever hear anybody talking about it, but you'll see, I'm going to show you why that's true. But there is a price to pay for using sparse estimators. There's a convenience to them, but they can have bad risk in the sense that we'll make precise. So we'll do all that next week. Any questions? All right. It looks to me like we can all fit in here now. So I think I'm going to tell the powers that be to clear the waiting list. Let me know if there's any problems.